8A is asking for us to look at the graph and explain why the component X is non-ohmic. So if something is ohmic, what that actually means is we have a constant resistance within the component. So if something is non-ohmic, it means the resistance is changing. And that is the answer for 8A. For 8B, so this one is the one that has the graph attached to it in 8A. And what we've got is a series circuit. We've got the component from the graph, and then we've added a variable resistor in series with an ammeter, and we've got 4.0 volts input into the circuit. So determine the resistance of the variable resistor R. So in order to do that, we're going to need to know a little bit more information. So first of all, I'm just going to remove this because I'm going to draw a couple of voltmeters across it. So we've got a voltmeter here, let's imagine, and that voltmeter is going to read a reading according to the graph where it crosses 20 milliamps. So if I go up here and have a look where it reads 20 milliamps, we're about here. And if I dot down, it's over halfway. It's probably about 2.3. So let's say that the voltage across here is going to be 2.3. So it means that the variable resistor is going to take the remaining. So it's got a 4.0 output into the circuit, minus the 2.3 that's already been taken by X, which means the variable resistor is taking 1.7. So 1.7 across here. And then it's asking for the resistance of the variable resistor. So we know that this is the voltage, and if we use V equals IR, then R equals V over I. So the voltage is 1.7. We just add the volts in there. 1.7 volts divided by 20 milliamps. Be very careful not to trip up there. And if we work that out, we get 85 ohms. Calculate the power dissipated for 8C. Well, power equals VI. So the voltage in the circuit is 4.0 multiplied by the current in the circuit at this value. So they are asking us to assume it's still the same current reading. Okay, that's an assumption you need to make because it's following through on the same question. So the power output is 0.08 watts. (8D). State the range of current that the ammeter can measure as the slider of the potential divider is moved from Q to P. Okay, so they've replaced component X by a potential divider circuit. And so the idea is that we've got this slider and it can move up and down this amount to provide different amounts of resistance so that we can read different voltages, if you like, and different current outputs from the input circuit. So the beauty of these is that the current can always go from 0. You just need to learn this, even if you don't understand the application of it. So it goes from 0 all the way to the maximum current that's supplied from the value of the output voltage. So we're back to component X. So we're going to go and have one more look at the graph and see what the current reading is when the voltage is all the way up to 4. So let's go ahead and do that now. So when the voltage is at 4, the current reading is 60 milliamps. So that means that the ammeter can read anything from 0 all the way to 60 milliamps. Make sure you've got the correct unit there for the mark. Okay. And so describe the advantage of the potential divider arrangement now. So the advantage of it is that you can get a greater range of readings for, greater range of current kind of readings. And this is because that's the first point. It's always the same answer for these for this question. Okay, so the advantage of it when it's talking about potential divider, always the same answer for 2 marks. Greater range of current readings because it allows the current to be 0 through the potential divider. It's really cool.